Our universe unfolds like a vast ocean of light and gravity, filled with galaxies spiraling through space and time. From the delicate arms of the Milky Way to the farthest threads of the cosmic web, we float within a silent, expanding sea of energy. But what if this immense expanse is merely a single layer, one universe among countless others, unseen but very real? For generations, humanity has looked up at the night sky with wonder. We've asked if there are other beings among the stars. But today, a more profound question arises. What if there are other realities entirely? Other universes with different laws, different histories, and perhaps different versions of ourselves. This idea, once relegated to myth or science fiction, now finds echoes in the equations of physics. The concept of the multiverse, the possibility that our universe is just one of many, has emerged from serious efforts to explain what we observe in the cosmos. From the rapid expansion that followed the Big Bang to the strange behavior of particles at the smallest scales, nature seems to whisper that our reality may not be all there is. The multiverse, if it exists, would be a vast collection of universes, each self-contained and independent. Some might look much like ours, filled with stars, galaxies, and life. Others might be unrecognizably different. In some, gravity might be too strong for stars to form. In others, time might move differently, or not at all. There could be places where light behaves strangely, or where the forces we know are replaced by others we cannot yet imagine. To picture the multiverse is to imagine a cosmic library where each book contains a unique version of a reality. Some volumes might share familiar themes, planets, atoms, consciousness, while others tell stories that obey entirely different rules. The diversity could be infinite, and we might only be reading one chapter. What makes this notion more than fantasy is its grounding in modern physics. The theory of cosmic inflation suggests that in the first fractions of a second after the Big Bang, space expanded at an incredible rate. In this rapid inflation, pockets of space could have become isolated, forming bubble universes, each with its own physical constants. Meanwhile, quantum mechanics proposes something equally strange. At the quantum level, particles can exist in multiple states at once. When measured or observed, a particle chooses a state. One interpretation suggests that all possible outcomes actually occur, each in a separate branching universe. In this view, the multiverse is not just a possibility, but a necessary result of how reality functions. This isn't just theoretical indulgence. Some physicists argue that without the multiverse, we cannot explain why the laws of physics in our universe are so finely tuned for life. Why is gravity not too strong, or electromagnetism not too weak? Why does the speed of light, or the mass of the electron, fall within the narrow range that allows atoms, chemistry, and biology to exist? In a multiverse filled with countless random configurations, it's not surprising that one universe, ours, has the right conditions for observers to ask such questions. But if these universes exist, could we ever detect them? Might they leave behind subtle traces, anomalies in cosmic radiation, strange alignments in deep space, or unexplained quantum effects? Could the oddities we sometimes observe be hints, however faint, of realms beyond? Theoretical models suggest that, under certain conditions, interactions between universes might occur. Some propose that black holes could serve as gateways. Others imagine regions of space where the boundaries between dimensions grow thin, doorways not made of metal or stone, but of warped space-time and hidden geometry. String theory, Another powerful framework in physics suggests that our universe may have more dimensions than the four we experience: length, width, height, and time. These extra dimensions could be compacted, curled so tightly that we cannot perceive them. But in extreme environments, near black holes or at high energies, they might become accessible, opening the door, quite literally, to other realities. What if there are portals, natural or even artificial, that lead from one universe to another? What if, deep within the fabric of space, there are passages connecting these vast, distinct realms? For now, these remain questions, but physics has taught us that yesterday's speculation can become tomorrow's discovery. Even without direct access, the multiverse changes how we think about existence. It challenges the idea of a single, absolute reality. It invites us to see our universe not as a solitary island, but as part of a vast, interconnected archipelago of possibility. And so we begin our journey. We will explore the theories, the evidence, and the imagination that surrounds this topic. We will peer into the depths of cosmology, quantum physics, and dimensional geometry, not to find all the answers, but to open the first of many doors. For now, one quiet question lingers. What might lie through such unseen thresholds? To understand how the multiverse might emerge from the universe we know, we must return to the very first instant of time, the moment our cosmos began. According to the most widely accepted model of cosmology, our universe was born in an event known as the Big Bang. But the Big Bang was not an explosion in space, it was the rapid expansion of space itself. In the first split second after this event, something extraordinary is believed to have occurred. A period of cosmic inflation. This was not just ordinary expansion, but an unimaginably fast swelling of space, an expansion so extreme that regions of the universe were stretched apart faster than the speed of light. During this time, quantum fluctuations, tiny, random variations in energy, were also stretched across vast distances, seeding the structure of the cosmos we observe today. This inflationary phase lasted only a fraction of a second, but its consequences were profound. Different regions of the inflating space may have experienced this expansion at slightly different rates. Some areas would have slowed down and formed what we now see as galaxies and clusters. Others may have continued to inflate, branching off into separate domains, forming isolated bubbles of space-time. Each of these bubbles could become a universe of its own, with distinct physical properties, constants, and perhaps even dimensions. In this view, our universe is simply one of countless such bubbles drifting in a vast cosmic foam. Each bubble is causally disconnected from the others, too far and too separate for light or matter to travel between them. This idea, called eternal inflation, suggests that inflation never truly ended. Instead, it continues in remote regions, constantly spawning new bubble universes. The multiverse in this model is not a fixed structure, but a dynamic and ongoing process. Like soap bubbles appearing endlessly in boiling water, new universes may form continuously. Why would these universes be different from one another? Because the fundamental parameters of nature, the strengths of forces, the masses of particles, the number of dimensions, could be set randomly in each bubble. One universe might allow atoms to form, while another collapses into chaos. Some might be lifeless voids, others fertile grounds for complexity. Support for this picture comes not from direct observation, but from how well the theory of inflation explains what we do observe. The uniformity of the cosmic microwave background, the faint afterglow of the Big Bang, is remarkably consistent across the sky, suggesting that regions now far apart were once in close contact. Inflation explains this. It also predicts the tiny variations we see in that background, ripples that became galaxies. These predictions have been confirmed by measurements from satellites like COBE, WMAP, and Planck. Inflation also offers an elegant solution to problems that once puzzled cosmologists, like why the universe appears so flat, or why it looks the same in all directions. But perhaps its most surprising consequence is the implication that our universe may not be unique. Still, eternal inflation is a theoretical framework. While it is consistent with current data, its predictions about other universes remain beyond our reach. These bubble universes, if they exist, are separated by inflating space that expands faster than light, making them forever inaccessible to us. Yet the concept changes how we interpret reality. If our universe is one bubble among many, then the fine-tuned laws we experience need no special explanation. They simply reflect the conditions within our particular bubble. Just as Earth is one planet among billions, our universe may be one domain among countless others. The bubble metaphor captures both the beauty and fragility of this idea. Each universe floats in a larger sea of space, delicate and isolated. Some may bump into one another, triggering collisions with unknown outcomes. Others drift alone. And somewhere within this foam, we find ourselves, conscious beings, wondering if there are others like us in other bubbles. As we move forward, we'll see how these ideas intersect with the strange realm of quantum mechanics. If inflation suggests many universes across space, then quantum theory hints at many universes branching within. Two perspectives emerging from different questions, both pointing toward the possibility of a multiverse. From the grand scale of cosmic inflation to the fine grain of quantum uncertainty, reality begins to look more layered than we once believed. And still, a deeper question lingers. Is our universe the rule or the exception? At the quantum level, reality behaves in ways that defy our everyday experience. Particles, the fundamental units of matter and energy, do not behave like solid objects. Instead, they exist in a state of superposition, a mathematical blend of multiple possibilities. A single electron, for example, does not sit in one specific place or move along one exact path. It can exist in several locations, follow several paths, spin in multiple directions, all at once. This phenomenon implies that until a particle is measured, its state remains undefined, not unknown, but truly not fixed. The act of observation appears to force a choice. The particle takes on a specific value, a definite position, a measurable spin. But what if, instead of collapsing into one outcome, the universe itself branches? This is the startling suggestion of the many worlds interpretation of quantum mechanics. Proposed in the 1950s by physicist Hugh Everett, it offers a bold view that all possible outcomes of a quantum event are realized, but in separate, non-communicating realities. When a quantum event occurs, say, a radioactive atom decaying or not decaying, both outcomes happen. One in our universe, and the other in a parallel version. Each time such an event occurs, the universe splits. According to this view, the entire cosmos is constantly branching. With every interaction, every decision, every moment where uncertainty is resolved, a new reality is born. These branches are not fantasy. They emerge from the same equations that describe quantum behavior in laboratories. The mathematics that governs tiny particles may, if taken seriously, imply that the universe is perpetually multiplying. This may seem abstract, but it touches our lives more than we imagine. Every decision we make, whether to turn left or right, to speak or remain silent, may correspond to a fork, not only in experience, but in reality itself. The many worlds theory doesn't just apply to particles. If consciousness is tied to quantum processes in the brain, then our choices may participate in this branching. This idea leads to profound reflections. In one reality, a traveler misses the train. In another, they catch it and meet someone who changes their life. In yet another, the train never existed at all. These are not alternate timelines from fiction. They are possibly real branches, each as valid as our own. We do not perceive them because the branches do not interfere. Once separated, they remain distinct. At the quantum level, the world is not a fixed stage, but a field of possibilities. Reality in this light is not singular, but layered, like the pages of a book being written all at once. Each possibility becomes its own narrative, moving forward independently. What we call history is merely the version we inhabit. Some physicists prefer interpretations that avoid this proliferation of worlds. They suggest that quantum uncertainty reflects incomplete knowledge, not genuine multiplicity. But the many worlds theory remains compelling because it removes the need for an observer to cause collapse. Instead, it lets the universe evolve unbroken, splitting cleanly whenever choices are made. This view also aligns with the conservation of information, a principle in physics stating that nothing is truly lost. In a branching universe, all outcomes are preserved. No possibility is erased. Rather, the cosmos retains every variation, every path not taken in a growing tree of realities. The metaphor of branching becomes even more powerful when visualized. Imagine the universe as a vast tree with its trunk rooted in the Big Bang. As time flows forward, each quantum event becomes a fork, a split into new limbs. Some grow wide, some narrow, some converge, others diverge forever. We live on one branch, unaware of the others, yet still part of the same tree. This vision challenges the simplicity of a single linear history. It invites us to see reality as fundamentally plural. We are not the only version of ourselves. Every choice we did not make, every chance we did not take, may still echo in another world. And still, these worlds are not accessible. The barriers between branches are not made of distance, but of decoherence. A quantum process that prevents overlapping realities from interfering. Once split, each version evolves independently, like separate melodies that once shared a note. Though the implications are staggering, the theory remains grounded in physics. The equations of quantum mechanics are among the most successful in science. They predict phenomena with extraordinary precision. If we take them seriously and follow their logic, the many worlds view becomes difficult to avoid. Of course, no current experiment can directly confirm the existence of other branches. But researchers are exploring ways to test whether quantum systems retain hidden correlations, traces of branching paths. Experiments with quantum computers, entangled particles, and high-precision measurements may one day reveal subtle fingerprints of parallel outcomes. At the quantum level, what we call the present may be a kind of cross-section, a slice through countless unfolding realities. And we, like particles, ride the wave of probabilities, only anchoring to a path when an outcome emerges. This vision of reality does not diminish the importance of choice. In fact, it may elevate it. Each decision creates not just consequences, but entire landscapes. In every moment, the universe blossoms anew. As we prepare to delve into string theory, the next piece in our exploration, we carry this image of a universe not static, but blooming, not singular, but branching. And in the silence between possibilities, we begin to wonder how deep the roots truly go. As we move deeper into the structure of reality, the picture becomes even more intricate. The familiar 4 dimensions, 3 of space and 1 of time, may not be the whole story. For decades, physicists have sought a unified theory, one that combines the laws of the very large, gravity and general relativity, with those of the very small, quantum mechanics. And one candidate has emerged with astonishing implications: string theory. At its core, string theory suggests that the fundamental building blocks of the universe are not particles, but tiny vibrating strings of energy. These strings are unimaginably small, so small that, to date, we have no way to observe them directly. But their vibrations determine the properties of everything in existence. A string vibrating in one way may appear as an electron. Another mode of vibration might produce a quark. Just as different notes come from different vibrations on a violin string, the essence of matter and force may arise from different patterns of these cosmic strings. This elegant idea requires more than just 4 dimensions. In order for the equations of string theory to work without contradictions, additional dimensions are needed. Not 5, not 6, but 10 or even 11 dimensions of space and time. Most of these dimensions are not extended like length or height, but are compactified, curled tightly upon themselves, folded into shapes smaller than any subatomic particle. To visualize this, imagine a garden hose. From a distance, it appears as a one-dimensional line, but up close, you can see that it has thickness, a coiled surface that loops around. In much the same way, these hidden dimensions could be coiled up at every point in space, influencing how strings vibrate, and thus how matter behaves. These extra dimensions are not mere abstractions. They influence the physics we observe, the strength of gravity, the behavior of particles, even the existence of fundamental forces. These may all be shaped by how the hidden dimensions are arranged. Different configurations of these dimensions could lead to different physical laws. Could these hidden layers hold the key to other worlds? In some versions of string theory, our universe is a 3-dimensional brain, a membrane, floating within a higher dimensional space called the bulk. Other brains might float nearby, parallel to ours, each potentially containing its own universe with its own physics. These universes would be hidden not by distance, but by separation in higher dimensions. We might be like shadows cast on a wall, unaware of the structures just beyond our frame. In this view, gravity is special. Unlike other forces, it may not be confined to our brain. It could leak into the higher dimensions or even travel between brains. This might explain why gravity is so weak compared to other forces. We experience only a fraction of it, and it raises a fascinating possibility that gravitational effects from other universes could, under certain conditions, influence ours. Some theorists speculate that collisions between brains might even cause events like the Big Bang. In this scenario, our universe was born when 2 higher dimensional surfaces slammed together, releasing vast amounts of energy and forming the space-time we inhabit. The mathematics of string theory is complex and abstract, often requiring dimensions and geometries far beyond intuition. Yet, it provides a framework where quantum mechanics and gravity can coexist, a long-sought goal in physics. And within this framework, the idea of multiple universes becomes not only plausible, but natural. These hidden dimensions may also become accessible in extreme environments, near black holes, where space and time are stretched to their limits, or in the high-energy conditions of the early universe. The compacted dimensions might briefly unfold, revealing new physics. Experiments with powerful particle accelerators, such as those at CERN, are probing these frontiers. Though we have not yet detected extra dimensions, researchers continue to search for subtle anomalies, deviations in energy, unexpected particle behavior, or signs of gravity behaving oddly at small scales. If discovered, these clues would revolutionize our understanding of space and time. They would suggest that our visible universe is just the surface of a deeper, richer structure, one shaped not only by the dimensions we see, but by those we do not. The metaphor of coiled threads is apt. Just as the threads of a tapestry lie hidden beneath the visible design shaping its patterns, the extra dimensions of string theory may weave the fabric of reality behind the scenes. We live on the surface, yet we are governed by what lies beneath. This insight expands the multiverse concept, no longer limited to distant bubbles or quantum branches. Other universes might be just next door, inaccessible not because they are far, but because they are folded away. A millimeter might separate them, or 1,000,000,000,000 blank lengths. The gap is not measured in space, but in dimensional direction. As we continue, we will explore how these ideas lead to new forms of multiverse speculation. If the shape of hidden dimensions can vary, then so can the physical laws they produce. We begin to imagine entire realities governed by different constants, different symmetries, and perhaps different forms of life. Through vibrating strings and hidden corridors, reality once again reveals itself to be more complex, more mysterious, and more interconnected than we once believed. And as always, a quiet question persists. What other forms might existence take just beyond the veil? Each universe, born from the chaotic sprawl of eternal inflation or split by quantum events, may come with its own unique recipe for reality. The familiar constants that shape our existence, gravity, the speed of light, the strength of electromagnetism, could take on entirely different values elsewhere. Even small shifts in these numbers would lead to radically transformed worlds, many of them unimaginable. In one such universe, gravity might be slightly weaker. It sounds benign, but the consequences would be profound. Stars might never ignite, their masses too small to trigger the nuclear fusion that powers them. Galaxies could disperse before they fully form. Without starlight, no warmth would exist, no heavy elements forged in stellar cores, no planets, and no life as we understand it. Now picture a reality where gravity is stronger. Matter clumps quickly, forming dense, short-lived stars that burn hot and vanish in flashes. Black holes proliferate. Time itself bends more steeply. In these universes, conditions change too fast for complex systems to arise. Chemistry, as we know it, may never stabilize. Consider a cosmos where the electromagnetic force is weaker. Atoms might fail to hold together, or stronger. Chemical bonds become too rigid, preventing molecular interactions. Water might not form. Carbon, the backbone of terrestrial life, might not exist. Instead of a world of oceans and clouds, there could be barren fields of inert dust, or landscapes dominated by strange fluids, metallic vapors, or crystalline plains. In some theoretical models, entire universes could be composed of exotic matter, substances we have never seen and can barely imagine. There could be planets made of pure neutronium, or clouds of plasma drifting in magnetic fields stronger than anything our instruments can detect. On such worlds, rain might fall as molten glass. Rivers could flow with acid instead of water. Skies might shimmer with radiation we cannot see. Some scenarios hint at astonishing diversity. Imagine a planet where gravity is weak enough for mountains to tower hundreds of kilometers high, or where the atmosphere glows with luminescent gases. On another, diamond storms might regularly crash through clouds, the result of carbon-rich chemistry under high pressure. These are not scenes from fantasy, but extrapolations grounded in physics, projections from changing the initial conditions. If life arises at all in such places, it would not resemble what we know. It might be built from silicon instead of carbon, using solvents other than water. Information could be stored in magnetic fields or pressure waves rather than DNA. Consciousness, if it exists, might be distributed, spread across clouds, oceans, or planetary crusts. Thought could be slow, deliberate, shaped by conditions that unfold over centuries. These are not idle speculations. Scientists studying astrobiology and artificial life already explore how life might adapt under alternate rules. The periodic table itself could be different in another universe, supporting chemistry that produces entirely unfamiliar possibilities. What seems improbable here might be inevitable elsewhere. Even time itself could behave differently. In some universes, it might move in discrete steps rather than flowing continuously. In others, it could loop or branch, creating layers of causality foreign to our experience. Entropy might run in reverse. Cause might follow effect. Perception, memory, and identity could be redefined in such domains. All of this stems from the idea that the multiverse contains every version of physical law allowed by mathematical consistency. Our universe is one outcome among a vast landscape of possibilities. Eternal inflation does not produce identical copies. It crafts variation. Each bubble universe forms with its own initial energy, its own vacuum state, its own symmetry breaking, and with those, its own fate. Some versions may be stillborn, expanding too quickly or collapsing too soon. Others may thrive for trillions of years, rich with complexity. And within that spectrum lie universes not just different, but potentially habitable. Strange, yes, but capable of sustaining ordered structures, perhaps even observers. If consciousness emerges there, it may never resemble ours. Yet, from its own perspective, it might ponder similar questions. What is this world? Why are its laws as they are? Might there be others? The diversity of potential realities invites humility. Our universe, rich and beautiful as it is, may not be special, just possible. Its laws are not ordained, but selected, perhaps randomly, perhaps as one solution in an infinite equation. From this understanding, we prepare to explore a deeper frontier, the idea that under certain conditions, connections between these realms may exist, not merely in theory, but through structures embedded in a very geometry of space. Portals, bridges, wormholes, these have long occupied the imagination. But could physics support them? Could the fabric of space-time itself allow shortcuts across realities? Before we step forward, the image lingers. A cosmos not uniform, but endlessly varied, where gravity bends differently, where time sings its own melody, where matter forms patterns no eye has seen. And still, the great question endures. Might we one day find the doorway to such a place? They drift silently in the vastness of space, invisible to the eye, yet profoundly influential. Black holes, among the most extreme objects in the universe, are places where gravity overwhelms all other forces. They are not merely dense stars or collapsed cores. They represent boundaries beyond which the known laws of physics begin to break down. A black hole forms when a massive star exhausts its fuel. Without radiation pressure to counteract its own mass, the star collapses under gravity, compressing into an incredibly small point known as a singularity. Around this central point lies the event horizon, the no-return boundary. Once crossed, not even light can escape. Time dilates, space distorts, and the fabric of reality bends toward the unknown. To an outside observer, an object falling into a black hole appears to slow as it nears the event horizon, never quite vanishing. But from the object's own perspective, it falls freely past that edge, entering a region of space and time so distorted that our concepts of direction, causality, and location may no longer apply. Inside, the gravitational field becomes infinitely strong, and so far impenetrable to science. The singularity at a black hole's heart is not a structure in space, but a failure of our equations. It marks a place where densities reach infinity and time collapses into a point. General relativity breaks down here, and quantum mechanics offers no clear guidance. This unresolved contradiction points to a missing link, perhaps a theory of quantum gravity that could unite the two frameworks. Some theories propose that black holes are not the end, but the bridge. The intense curvature of space might tunnel through to another region of the universe, or even to a different universe entirely. In this speculative framework, black holes could be entrances to wormholes, with their counterpart ends emerging as white holes, hypothetical objects that expel matter, the inverse of black holes. White holes have never been observed. Their existence remains theoretical, and many physicists doubt whether they could form naturally. But the math permits them. In certain solutions to Einstein's equations, a black hole connects to a white hole through a wormhole-like passage. Whether such a structure could remain stable or even allow transit remains an open question. Some cosmologists speculate that the interior of a black hole might seed a new universe. If conditions inside reach a critical threshold, the compression could trigger a new Big Bang, isolated from its parent. In this model, each black hole could contain an entire reality, causally disconnected from our own. We might be living inside such a universe now, never aware of the cosmic parent that birthed it. Despite their elusiveness, black holes leave evidence. Their immense gravity distorts the motion of nearby stars. Gas spiraling into them heats up and emits X-rays. And in 2019, the Event Horizon Telescope delivered a historic milestone. The first direct image of a black hole's shadow, revealing a glowing ring of plasma around a dark core in the galaxy M87. That image, built from data collected by a planet-sized array of radio telescopes, marked a triumph of human ingenuity, a glimpse at the edge of the abyss. Yet the true nature of what lies beyond that glowing ring remains hidden. Inside, no signals can escape, no probe can return. The secrets of the singularity remain sealed shrouded behind the event horizon until physics finds a new key. Quantum theory introduces further puzzles. The question of information loss, whether data about infalling matter is destroyed, challenges our understanding of unitarity and conservation. Some proposals suggest that information may be preserved on the event horizon, encoded in surface vibrations or soft hair. Others invoke holographic principles, in which reality itself is a projection from lower dimensions. These ideas, rich with implication, hint at a deeper connection between space, time, gravity, and quantum behavior. Some physicists even suggest that black holes are fundamental to how the universe processes information, that they are not just astrophysical curiosities, but computational engines, compressing and transforming complexity. Could the depths of a black hole lead somewhere else? Could the singularity be a junction, not a wall, but a threshold? So far, we lack the tools to explore it, but the possibility stirs imagination and invites new theories. It is not only theoretical physicists who are drawn to black holes. Science fiction writers, artists, and filmmakers have long explored their symbolic and narrative power. In these stories, black holes are gateways, portals not only through space, but through understanding. They represent the ultimate unknown, the place where meaning unravels and must be rebuilt. From a practical standpoint, interstellar travel to a black hole remains beyond reach. The closest known black hole lies thousands of light years away. The gravitational forces near its horizon would stretch and compress matter in ways no human could survive. Yet, in mathematics, and perhaps in far future technology, the idea remains tantalizing. Some advanced civilizations, if they exist, might find ways to harness black holes as energy sources, data storage, or even transportation hubs. The rotational energy of a spinning black hole could, in principle, be extracted. The curvature of space around it might offer shortcuts, if stabilized. We are far from such capabilities, but not from the questions they raise. Ultimately, black holes remind us that the universe is not fully mapped. They are the blank spaces on the cosmic chart, the regions labeled "Here be dragons." They humble us, confront us, and invite us forward. Through wormholes, they might lead to other places. Through singularities, they might birth new realities. And through their mystery, they might reveal deeper truths. For now, they remain dark hearts of gravity, holding within them the edge of what we know. And just beyond that edge, perhaps, the next great journey begins. To gaze up at the stars is to yearn, not only to understand, but to reach. For as long as humans have existed, the night sky has inspired dreams of distant worlds, voyages across the cosmic ocean, and the possibility of travel beyond our solar system. Today, those dreams persist, but they face the cold realities of distance, energy, and time. The nearest star system to Earth, Alpha Centauri, lies over 4 light years away. That means even light, traveling at nearly 300,000 kilometers per second, takes more than 4 years to get there. Our fastest spacecraft would require tens of thousands of years to cross that span. The gulf between stars is not only vast, it is overwhelming. And yet, the question remains, could we go? Could intelligent beings, whether human or otherwise, find a way to bridge that cosmic void? Physics does not forbid interstellar travel. It simply makes it very, very hard. Several methods have been proposed. One is the use of antimatter propulsion. When matter and antimatter meet, they annihilate, releasing pure energy, far more efficient than chemical rockets. A spacecraft powered this way could, in theory, reach significant fractions of light speed. But antimatter is difficult to produce, harder to store, and currently exists only in tiny amounts. To fuel even a modest journey, we would need engineering capabilities far beyond our present grasp. Another possibility is the solar sail. Like a sailboat harnessing wind, a spacecraft could unfurl an ultra-thin reflective surface, pushed by photons from a powerful laser or the sun itself. The pressure of light, though gentle, is constant, and over time, it could accelerate a lightweight craft to impressive speeds. This method has already been tested in miniature. One day, it could propel probes to nearby stars. There are more speculative ideas: fusion drives that mimic the reactions of the sun, particle beam propulsion, even theoretical engines based on warped space-time. Some designs, like the Alcubierre drive, imagine compressing space ahead of a craft and expanding it behind, effectively moving without crossing space in the usual sense. But these remain in the realm of theory, dependent on exotic physics and negative energy. Distance, however, is not the only challenge. Time itself behaves strangely when speeds increase or when gravity becomes intense. According to Einstein's theory of relativity, time slows down for an object moving close to light speed or deep within a gravitational well. This phenomenon, known as time dilation, has been confirmed by countless experiments. Imagine a spacecraft traveling to Proxima Centauri at 90% the speed of light. From Earth's perspective, the journey takes about 4.6 years. But for those on board, due to time dilation, the experience would be shorter, perhaps only 2 years. The faster you travel, the more pronounced the effect. At speeds near light, years might pass on Earth, while only months pass for the traveler. The same applies near massive objects. Near a black hole where gravity is extreme, time ticks more slowly. In principle, an astronaut orbiting such a region might return to find that centuries have passed elsewhere. This time, stretching is not illusion. It is physical reality built into the geometry of space-time. How might such journeys alter our timeline? In the realm of science fiction, time travel is often depicted as a leap to the past or future. But in science fact, time travel forward is not only possible, it is unavoidable. Every fast-moving particle, every satellite, every GPS clock experiences tiny but measurable differences in time. Scaling this up to interstellar travel could result in profound shifts between the traveler's clock and that of the homeworld. This raises questions, not only technological, but philosophical. If a person departs on a near light-speed voyage and returns centuries later, what awaits them? Their culture? Their language? Their world? The journey is not merely through space, but through history. Practical considerations also loom large. Human bodies are not built for long-term spaceflight. Exposure to cosmic radiation, psychological isolation, and the challenges of sustaining life support systems over decades or centuries remain unsolved problems. Robotics and AI might help, but the dream of crude interstellar travel still lies far ahead. Communication becomes another obstacle. A signal to Alpha Centauri takes over 4 years, one way. Real-time conversations are impossible. A mission to even the nearest stars would be, in many ways, an expedition into silence. Still, the idea persists. Projects like Breakthrough Starshot envision launching gram-scale probes at a fraction of light speed, using powerful lasers. Such probes could reach nearby stars in decades, sending back data across the void. These efforts, though modest, represent the first true steps toward other suns. Interstellar travel may also intertwine with the multiverse. If wormholes exist, and if they can be stabilized, they might offer a shortcut not only between distant regions of our own universe, but between entirely different universes. Such corridors could, in theory, bypass both space and time, delivering a traveler to a realm governed by different laws. Yet the energy required to open, sustain, or even locate such a wormhole is staggering. For now, we remain grounded, not by imagination, but by the limits of what we can build. Still, we've made progress. Humans have left the solar system. Voyager 1, launched in 1977, now drifts through interstellar space, carrying a golden record with greetings and music from Earth. It moves slowly, but it endures. It is the first emissary of our world to the stars. In the future, fusion reactors, antimatter factories, or even harnessed black holes might power faster ships. Our descendants, biological or digital, might sleep through centuries or not sleep at all. They may be born in space, live in transit, and arrive on shores we cannot now imagine. The journey between stars is daunting, but not impossible. The physics is hard, but not closed. The light from Alpha Centauri still reaches us, and one day we may return the gesture. Next, we explore the deeper implications of traveling not just forward in time, but between realities, histories, and possibilities. For now, we look outward and forward. Throughout history, tales of time travelers have surfaced like echoes from an uncertain past, or perhaps from possible futures. These stories often begin not in laboratories or observatories, but in anonymous forums, obscure archives, or the baffled memories of eyewitnesses. Though lacking scientific proof, they linger, casting long shadows across our understanding of time. One of the most discussed figures is John Titor, a name that emerged on early internet forums in the year 2000. Claiming to be a soldier from the year 2036, Titor described a future America fractured by civil conflict and nuclear war. He said he was sent back to retrieve a vintage IBM computer needed to debug legacy systems. His posts included diagrams, predictions, and reflections on time travel theory. Many of his forecasts did not materialize, yet the detail, tone, and apparent consistency of his account inspired fascination and suspicion. Was it an elaborate hoax, a fictional exercise, or something else entirely? Then there is the curious case of the man from Taured. In 1954, at Haneda Airport in Tokyo, a European-looking man reportedly arrived with a passport from a country no one had ever heard of. Taured. The document seemed genuine. The man claimed it lay between France and Spain. Confused, officials detained him. But by morning, he had vanished from his locked hotel room, leaving behind no trace. The story is unverified and may be apocryphal. Still, it remains one of the more enduring anecdotes tied to alternate realities or temporal anomalies. Other accounts center on anomalous photographs. A famous image from the 1940s appears to show a man in sunglasses and modern clothing amid a crowd dressed in period fashion. Dubbed the time-traveling hipster, the photo has been scrutinized, explained, and dismissed, but it still captures the imagination. Could such artifacts reveal slippages in time? Or are they just misunderstood moments frozen in film? These tales, while lacking empirical support, echo ancient human concerns. They raise questions about fate, causality, and the nature of reality. If time travel were possible, could someone visit a past without altering it? What if their presence changes events? Here lies the famous grandfather paradox. If you travel back and prevent your own grandfather from meeting your grandmother, would you still be born? One way to resolve the paradox is the idea of parallel timelines. In this view, the traveler's actions do not rewrite history, but branch it, creating a new sequence of events in a separate universe. The original timeline remains untouched. Another proposal involves self-consistency loops, where any action taken by the traveler was always part of history, ensuring no contradictions. Both concepts, though speculative, emerge from real mathematical solutions in relativity and quantum mechanics. Not all stories are about people. Some involve devices, alleged machines capable of peering into the past or future. One such example is the chronovisor, supposedly built in secret by Vatican scientists in the 20th century. Described in a book by Father Francois Brune, the device allegedly used electromagnetic waves to view historical events like the crucifixion. According to the story, the device was dismantled or hidden, its potential deemed too dangerous. No evidence has ever surfaced. The tale reads more like allegory than physics. Skepticism is healthy. None of these accounts meet scientific standards of proof. There are no verified artifacts, no repeatable phenomena, no independent confirmations. But the persistence of these stories says something about us. Not about time travel, but about our yearning to understand it. They give shape to uncertainties. They allow thought experiments in disguise. And sometimes they foreshadow ideas that science may one day explore with rigor. Einstein himself was once ridiculed for proposing time as a dimension subject to curvature and relativity. Today, GPS systems correct for relativistic time shifts every second. In a way, these tales humanize time travel. They pull it from the realm of tensors and metrics into bars, airports, attics, and archives. They populate it with flawed narrators, mysterious documents, and unanswered questions. Whether true or not, they form a mirror, reflecting both our hopes and our fears about what might lie beyond the now. They also act as a bridge. From speculative devices and internet legends, the journey continues to concepts like hyperspace, extra-dimensional travel, and the geometry of realities we cannot yet reach. And so, the next chapter begins. The idea of hyperspace has long captivated the human imagination, not just as a science fiction device for faster-than-light travel, but as a real mathematical possibility. A domain beyond the familiar four dimensions of space and time, where shortcuts might exist between distant points in the universe. At its core, hyperspace is a theoretical construct, a space of higher dimensions, invoked to explain why gravity is weaker than the other fundamental forces, or how particles behave in string theory. In this framework, our universe is like a membrane or brain floating in a larger multidimensional arena. While we are confined to 3 dimensions of space and 1 of time, the laws of physics may extend into 6 or 7 additional dimensions, compactified or folded so tightly that they remain unseen. The analogy often used is that of a 2-dimensional being living on a sheet of paper, unable to perceive a 3rd dimension. To such a creature, a sphere passing through the sheet appears first as a dot, then a growing circle, then a shrinking one, never revealing its full shape. Likewise, our universe may be part of a much broader geometric structure, of which we perceive only a slice. General relativity does not forbid higher dimensions. In fact, its equations can accommodate them. These extra dimensions, if real, might be small and curled up, existing at scales a trillion times smaller than an atom. Or they might be large and hidden, separated from us by subtle physical barriers. The challenge is detecting them. This is where CERN comes in, the European Organization for Nuclear Research, home to the Large Hadron Collider, LHC. Beneath the French-Swiss border, a 27-kilometer ring accelerates protons to near light speed and smashes them together, recreating conditions similar to those in the early universe, to those just after the Big Bang. One goal of these collisions is to probe the existence of extra dimensions. If space truly contains more than 3 spatial dimensions, energy could leak into them during high-energy impacts. This would cause detectable anomalies, missing energy, altered particle paths, or even the creation of microscopic black holes. These black holes, if produced, would evaporate almost instantly via Hawking radiation. They pose no danger, but their detection would be revolutionary. Direct evidence that gravity, and perhaps space itself, extends beyond the observable. So far, no such anomalies have been found. The energies required may be even greater than what the LHC can currently provide. But future colliders with higher power and sensitivity may one day reach the necessary thresholds. Some popular myths link CERN's experiments to fears of doomsday, that the collider could create a black hole that swallows the Earth, or open a portal to another dimension. These claims, while dramatic, have no basis in physics. Every known calculation, safety study, and real-world observation confirms the safety of these experiments. The Earth is constantly bombarded by cosmic rays, particles with energies far exceeding those in the LHC. If such collisions were dangerous, they would have already produced catastrophic effects. They have not. Hyperspace, in this light, is not a realm to fear, but one to study, a possible extension of geometry, a frontier where particles and forces might behave differently, where gravity might bleed and space might twist into forms we cannot yet imagine. Some interpretations of string theory suggest that particles are not point-like, but vibrating strings. The way these strings vibrate determines the type of particle, its mass, charge, and interactions. But for the math to work, these strings must vibrate not in 4 dimensions, but in 10 or 11. The extra dimensions provide room for the harmonies of the universe to unfold. Whether these dimensions are real or just useful scaffolding for equations remains to be seen. But the search continues, not only at CERN, but in satellites measuring gravitational waves, in laboratories testing the inverse square law of gravity at tiny scales, and in the minds of theorists seeking to unite general relativity with quantum mechanics. If hyperspace exists, then perhaps travel across vast cosmic distances is not about speed, but about geometry, about folding space, bridging points, bending roots, the way a higher being might lift 2 points on a page and press them together. This view challenges our intuition. We are creatures born in 3-dimensional space, moving forward through time. But mathematics suggests more may exist, and in the corridors of particle accelerators, we may be glimpsing the scaffolding of a larger cosmos. CERN does not open portals, but it does open windows. into the smallest scales of reality, and perhaps, just perhaps, into the shape of dimensions beyond. From here, we move toward the even stranger edge, where science meets story, where evidence blurs with experience, into the realm of the unexplained, paranormal phenomena, and their potential ties to parallel worlds. Across cultures and centuries, humanity has reported experiences that defy explanation. Apparitions in the night, whispers with no speaker, objects moving without cause. These phenomena, commonly labeled as paranormal, have long challenged the boundaries between belief, perception, and science. While most have conventional explanations, some persist at the edge, tempting the mind with echoes of something else. One enduring interpretation suggests that what we call ghosts or hauntings are not spirits of the dead, but resonances of time or space, echoes from other dimensions or overlapping timelines. Though speculative, this idea has gained attention as theories of parallel universes and higher dimensions become more widely known. Consider the reports from Gettysburg, the site of one of the bloodiest battles in American history. Visitors claim to hear gunfire, see spectral soldiers, or witness replays of battle scenes, described with eerie precision. Some suggest these are emotional imprints, a sort of environmental recording played back under the right conditions. Others wonder whether tears in the fabric of time, tiny temporary rifts, might allow glimpses into a parallel moment. In Spain, the village of Belmez de la Moraleda became famous in the 1970s when faces began to appear on the concrete kitchen floor of a family home. Known as the Belmez faces, these images seem to change over time, watched by researchers and locals alike. Some argued they were hoaxes or chemical reactions. Others claimed they defied all known explanation. While the evidence leans heavily toward mundane causes, the persistence of the images stirred debates about consciousness, reality, and perception. Then there are tales of time slips, anomalous experiences where individuals suddenly find themselves in the past or future, if only briefly. One frequently cited account involves travelers on a French road who claim to enter a hotel with early 20th century furnishings, only to find it gone the next day. Others speak of old-fashioned cars, clothing, or language witnessed in otherwise modern settings. Such stories are difficult to verify. Memory is fallible. Stress, fatigue, or expectation can distort perception. Psychological priming, such as visiting a known haunted site, can enhance suggestibility. But some researchers ask whether these experiences are entirely internal, or whether environmental factors, such as electromagnetic fields or infrasound, might influence the brain in ways we do not fully understand. Science offers grounded interpretations. Pareidolia, for instance, is the tendency to see patterns, especially faces, where none exist. It explains many sightings of ghostly figures in windows, walls, or shadows. Sleep paralysis accounts for reports of immobility and sensed presence. Hallucinations can result from sleep deprivation, neurological conditions, or medication. In many cases, the mind, under stress or expectation, constructs a narrative that feels real. Still, these explanations do not address every report. In a few cases, multiple witnesses, sometimes in broad daylight, have described the same anomaly. No instruments detect anything, and the event never repeats. Are these errors of observation, or glimpses into something transient just beyond reach? Some theoretical physicists have speculated that quantum fluctuations, or even brain-world interactions, might occasionally produce sensory artifacts. These would not be ghosts, but dimensional noise, random interference from adjacent realities. Just as a radio picks up faint signals from neighboring stations, perhaps the brain, under rare conditions, becomes sensitive to overlapping timelines. Yet, there is no testable model for this. The math is complex, the predictions vague, and so science maintains skepticism. Without reproducible evidence, such claims remain anecdotes. Fascinating, yes, but outside the domain of demonstrable truth. But it is worth noting that many paranormal events later found scientific footing. Ball lightning was once a myth. Meteorites were dismissed as fantasy. Deep-sea life was considered impossible. In each case, belief preceded evidence by decades, even centuries. Today, the intersection between perception, environment, and physics is more nuanced. Researchers explore how magnetic fields affect cognition, how geology influences mood, how architecture shapes emotion. What feels like a haunting might be an interplay of design, expectation, and brain chemistry. Yet mystery persists. Humans are story-driven creatures. We seek meaning in the strange, the unexplained, and sometimes that quest opens new avenues of understanding. Whether ghosts are echoes of trauma, misfires in the brain, or glimpses across dimensions, they reflect a deeper curiosity about what lies beyond the veil of the known. Paranormal tales may not be proof of alternate dimensions, but they mirror our wonder, our fear, and our longing to connect with something larger. They remind us that perception is not always reality, and that reality may be stranger than we think. From here, we turn not just to what is seen, but to what is felt, to the subtle effects of other realities on ours, to anomalies in time, memory, and consciousness. In the soft terrain between perception and reality lie phenomena that intrigue both scientists and storytellers. Some moments feel familiar without cause. Some memories are shared yet provably false. Some visions arise when life itself flickers. These experiences, often labeled as illusions, anomalies, or awakenings, invite deep reflection. Are there flaws in human memory, or fleeting glimpses of something beyond? The Mandela Effect is named for a curious observation that many people distinctly recall Nelson Mandela dying in prison during the 1980s, though in reality, he passed away in 2013. This collective misremembering isn't isolated. Across the internet, thousands report shared inaccuracies, the spelling of Berenstain Bears, the number of US states, or the phrasing of iconic movie quotes. One oft-cited example is Darth Vader's line in Star Wars. Many remember, "Luke, I am your father." But the actual quote is, "No, I am your father." From a cognitive standpoint, these errors stem from constructive memory, where the brain fills gaps using logic, pattern, and social cues. Memories are not exact recordings. They are reconstructions, constantly updated and reshaped. In group settings, misremembered facts can spread rapidly, reinforced through repetition and confidence. Yet some theorists suggest a more exotic possibility, that the Mandela Effect reflects overlaps between parallel realities. Perhaps in one timeline, Mandela died in prison. In another, he didn't. The confusion then arises when consciousness somehow shifts between these layers, bringing residual memory from a prior universe. Science remains skeptical. No mechanism is known for such shifts, and all evidence to date supports cognitive origins. But the phenomenon underscores the deeper truth, that what we know is often more fragile than we believe. Another frontier of altered perception lies in near-death experiences, NDS. reported across cultures and ages. These include sensations of floating, tunnels of light, meetings with deceased relatives, or panoramic life reviews. Common elements appear even when the experiences have no exposure to similar stories. Neurology provides a framework. During extreme physiological stress, like cardiac arrest or oxygen deprivation, the brain may activate pathways that create vivid imagery. The tunnel effect may result from peripheral retinal cells shutting down. Feelings of euphoria may stem from endorphin release. Temporal lobe activity might generate life flashes or the sensation of detachment. Still, NDEs are reported with clarity and conviction. Some patients describe events in the operating room while technically unconscious. Others return with a transformed worldview. Whether purely neural or not, these experiences shape lives. Some researchers propose that NDEs are not falsehoods, but a unique intersection of biology and consciousness. In rare moments, the brain may access states normally beyond waking awareness. This doesn't require alternate dimensions, but it opens questions about the brain's latent capacity and whether consciousness can extend beyond the body. Then there is déjà vu, that sudden, inexplicable feeling that one has lived this moment before. It is brief, elusive, and common. Nearly 2/3 of people report experiencing it. Neuroscience attributes déjà vu to temporal lobe mismatches, where signals from the brain's memory systems are misrouted. A current experience may be flagged as familiar because it passes through circuits usually associated with recall. Alternatively, slight delays between visual and auditory processing can create a false sense of repetition. But to some, déjà vu feels more than mechanical. It feels sacred, significant, as if reality were echoing. If time is not linear, and if the multiverse is real, then perhaps déjà vu is a resonance across nearby timelines, a brief moment when two versions of ourselves align. Once again, no evidence confirms this, but the emotional weight of the experience cannot be dismissed. It hints at the subjective mystery of being, a consciousness aware of itself in time. What unites these phenomena is their challenge to certainty. They remind us that the mind, for all its brilliance, is not infallible. It can conjure ghosts, reframe memory, and fabricate familiarity. But perhaps that same mind, when stretched to its limits, begins to brush against something larger. Could these anomalies be traces of deeper structures, connections not yet understood? Could they be like shadows cast by unseen geometry, hints of dimensions or timelines just out of reach? Or are they simply reflections of the brain exploring its own boundaries, inventing meaning where none exists? Either way, the mystery remains. And from these moments, whether sparked by memory, trauma, or the edge of life, we glimpse something fragile yet profound. What does it mean when many remember what never was? As we continue, we turn from fleeting sensations to the places themselves. The locations tied to these anomalies, spots where myth, mystery, and science converge. Scattered across the earth are places long associated with mystery, disappearance, and transformation. These sites, whether shaped by nature, culture, or legend, have stirred speculation that they may mark locations where the boundary between dimensions grows thin. The most widely recognized of these is the Bermuda Triangle, a region loosely defined by points near Florida, Bermuda, and Puerto Rico. Since the mid-20th century, it has gained notoriety for reports of aircraft and ships vanishing under unclear circumstances. the disappearance of Flight 19 in 1945, a group of US Navy bombers on a training mission, ignited decades of fascination. Pilots reported compass failures and disorientation before losing contact. Explanations range from mundane to extraordinary. Meteorologists point to sudden storms, rogue waves, and waterspouts. Navigational errors in a region with few landmarks are common. Geologists have proposed that methane hydrate eruptions from the ocean floor could disrupt buoyancy and disable engines. While these theories cover most incidents, the persistence of mystery keeps the idea alive that something stranger might be at play. A hidden portal, a temporal rift, or a dimensional fold. Thousands of kilometers away lies Sedona, Arizona, famed for its striking red rock formations and so-called energy vortices. These are locations where some visitors report sensations of heightened awareness, spiritual clarity, or subtle forces moving through their bodies. Though no instrument has confirmed such energy fields, Sedona attracts thousands seeking healing, inspiration, or contact with something beyond. Skeptics argue these effects are psychological, stimulated by expectation, awe at the landscape, or group influence. But others note the area's unusual magnetic patterns and high quartz content. Could certain geological features interact with consciousness in ways not yet understood? Across the Atlantic, Stonehenge rises from the Salisbury Plain, its massive stones aligned with solstices and celestial events. Its true purpose remains debated. A ceremonial site, an astronomical calendar, a burial ground. Some researchers propose that such alignments may tap into deeper natural rhythms, an ancient technology lost to modern understanding. Others believe the site marks a node where cosmic energies concentrate, potentially serving as a gateway point. In the highlands of Peru rests Aramumuru, a flat rock face with a mysterious door-like indentation. Local legends say Incan priests fleeing Spanish conquest vanished through this portal carrying sacred knowledge. They speak of the Gate of the Gods, a passage activated by a golden disc, long lost to history. Visitors today report strange dreams, chills, or shifts in perception while standing before the stone. Geologists call it a natural formation. No mechanisms or chambers lie behind it. And yet, the symbolic pull of such locations cannot be dismissed. Across time, cultures have marked certain landscapes as sacred thresholds, places where the sky meets the earth, where time folds, where gods once walked. Other sites echo this idea. Mount Shasta in California, linked to legends of hidden civilizations. The Devil's Tower in Wyoming, rising like a solitary sentinel. Japan's Aokigahara forest, where silence feels oppressive. Or Uluru in Australia, central to Aboriginal cosmology and said to pulse with ancestral energy. What connects these places is not proof, but pattern. Stories of strange sensations, reports of vanishing time, lights, sounds, or visions. Often, science offers plausible answers. Magnetic anomalies, weather effects, psychological priming. But occasionally, something lingers, an experience that resists full dismissal. Modern mapping tools, satellite imaging, and geomagnetic surveys have refined our understanding of Earth's structure. No hidden doorways have been found. But the pull of these locations persists not because of what we can measure, but because of what we feel when we stand there. Might our planet, in rare pockets, act as a lens for deeper reality? Could alignment of geology consciousness and history momentarily thin the veil? No instrument confirms it, but no instrument captures awe either. Such places remind us that mystery is not always distant. It lies in the soil beneath our feet, in stones shaped by wind and time, in tales whispered across generations. Perhaps the question is not whether these sites are portals, but why we keep returning to them. Next, we lift our gaze to the skies, to unexplained objects that dart and hover, to encounters claimed across decades. We turn to the enduring question of UFOs and their place within the multiverse. For decades, sightings of unidentified flying objects have stirred a curious mix of fascination, fear, and debate. From blurred photographs and radar anomalies to eyewitness accounts by trained pilots, the phenomenon has persisted, not as proof of visitors from beyond, but as a riddle straddling the line between the observable and the unexplained. The Roswell incident of 1947 remains a foundational mythos. After reports of a crash and recovered debris near Roswell, New Mexico, the US military first claimed to have found a flying disc, then quickly retracted the statement. Official explanations later pointed to weather balloons, specifically part of Project Mogul, an effort to detect Soviet nuclear tests. Yet for many, the inconsistency fueled suspicion. Testimonies from locals, including claims of alien bodies and secret transports, deepened the legend. In more recent times, the release of Pentagon-confirmed videos, such as the 2004 Tic Tac encounter off the coast of California, has reignited public interest. Pilots described objects that moved with no visible propulsion, changed direction instantly, and seemed to defy inertia. These movements challenge known physics. No sonic booms, no heat signatures, no trails. Traditional explanations struggle. Misidentified aircraft, atmospheric phenomena, optical illusions, or glitches in radar data account for many cases. But some incidents remain unresolved, resisting dismissal, yet eluding confirmation. This has opened the door for alternative frameworks. One of the more intriguing is the interdimensional hypothesis. Unlike the conventional view of UFOs as spacecraft from distant stars, this theory posits that they originate not from elsewhere in space, but from elsewhere in reality. They are not aliens in the traditional sense, but entities from adjacent dimensions or parallel timelines, briefly intersecting with our own. Thinkers like Jacques Vallée, a computer scientist and former NASA consultant, have long promoted this view. Vallée noted that UFO encounters often have symbolic, even absurd qualities, closer to folklore than space travel. He compared them to historical tales of fairies, jinn, and spirits, beings that appear, vanish, and defy consistent explanation. To him, UFOs may be manifestations from a layer of reality that interacts with human consciousness. John Keel, author of the Mothman Prophecies, went further. He proposed that what we call aliens, monsters, or ghosts may all stem from the same source, a non-human intelligence that coexists with us in a space we do not yet perceive. These entities could access our world through windows, fluctuations, or distortions, brief connections between dimensions. Supporters of the interdimensional model point to patterns. UFOs appear and vanish instantly, often leaving no physical trace. They shift shapes, produce electromagnetic disturbances, and sometimes seem to respond to human attention. Such behaviors align more with phenomena slipping across boundaries than with structured missions from other planets. Skeptics argue that these interpretations overreach, that they project meaning onto anomalies, creating narratives from noise. Science demands repeatability, and UFOs rarely cooperate. No artifact has been recovered, no technology verified, no biology examined. While governments admit interest, especially regarding flight safety and national security, they have not confirmed any non-human origin, but the mystery persists. Surveys show that significant portions of the population believe we are not alone. More compelling is the belief that some encounters may not be extraterrestrial, but extra-dimensional. Could our universe be one of many, each layered and slightly misaligned? And could certain conditions, locations, or states of consciousness allow for brief bleed-throughs, moments when realities touch? If so, the UFO phenomenon might not be about travel across space, but about access across domains. Not about propulsion, but about resonance. Not a physical journey, but a perceptual intrusion. From a physics perspective, higher dimensional space is not fiction. Theoretical frameworks like string theory require up to 11 dimensions. Most are compacted, invisible to us. But what if some are accessible, momentarily, unpredictably, incompletely? This would explain the ephemeral, inconsistent, often dreamlike nature of sightings. It would explain why entities seem to defy mass, logic, or linear time. It would suggest that what we call craft may be projections, not vehicles, dimensional echoes, rather than machines. Still, science demands more than elegance. It requires evidence. Until then, we are left with stories of spinning lights, impossible movements, and sudden disappearances. We are left with radar blips, confused pilots, and open skies. And we are left with a question that grows more layered as physics grows stranger. Are we alone in the universe? Or simply unaware of who or what shares our space? The next consideration brings us closer to that question. From interdimensional craft to the beings said to operate them, and from theories of alien life to the possibility that reality itself is a simulation, the inquiry deepens. If the multiverse exists, and if dimensions intersect, diverge, or echo, then the question of alien life becomes far larger than whether we are alone in this universe. It becomes a meditation on life in all possible forms, across all possible realities. Traditional portrayals of extraterrestrials imagine humanoid creatures with elongated limbs, gray skin, and large dark eyes. But in a multiversal view, life could manifest in radically different architectures. Some beings may be gelatinous, formless, thriving in oceans of methane. Others might exist as plasma currents tethered to magnetic fields. Some might be composed of pure information, their awareness distributed like a neural net across an entire planet. There could be species that perceive time in reverse, or whose biology is quantum entangled across dimensions. The deeper the multiverse extends, the more it suggests that life is not rare, but inevitable. The constants we consider finely tuned, like the strength of gravity or the mass of the electron, may vary from universe to universe. In most, conditions may be inhospitable. But with infinite diversity, there must be some where life not only exists, but thrives, in forms we cannot begin to imagine. One framework that has emerged from such reflection is the simulation hypothesis. Famously argued by philosopher Nick Bostrom, it suggests that our universe may be an artificial construct, a simulation designed by a higher intelligence, whether alien, posthuman, or unknown. The logic is disarmingly simple. If any civilization survives long enough to create realistic simulations of their past or alternate realities, then the number of simulated beings would vastly outnumber the number of originals. Statistically, we are more likely to be in one of the simulations than in the base reality. There are no proofs, only clues. The apparent fine-tuning of universal constants, the quantum tendency for outcomes to collapse only when observed, the pixel-like granularity of space-time at the Planck scale, all hint at a deeper structure that may not be physical in the traditional sense. Some physicists describe the universe as computational, unfolding according to informational rules. If true, then reality is not the bottom layer. It is a surface, a rendered environment, and we are the observers within it, either participants or projections, depending on the lens. But does it matter whether we live in a universe or a simulation, in a single world or infinite reflections? The mystery remains profound. We are here, we ask, we feel. For centuries, humanity has gazed upward in wonder, unsure what lies beyond. We have invented stories, drawn maps of stars, sent signals into the void. We have imagined others like us and utterly unlike us. And we have wrestled with the silence. If portals were to open, revealing alien minds, other versions of ourselves, or watchers behind the code, how would we respond? Perhaps not with answers, but with deeper questions, with humility. One can imagine transitions not unlike death, where the boundary between realities fades and something new emerges. Not as an ending, but as a shift in perception, like moving from one layer to another, from one frequency to the next. Such speculation is not science, but it is not meaningless. It reflects our desire to understand our place, to know whether we are isolated sparks or notes in a symphony of worlds. In contemplating the multiverse, we reflect not just on cosmology, but on a consciousness, meaning, and the unknown. And as we close this long journey, from inflationary bubbles and quantum forks to wormholes, black holes, and sacred ground, we do not end with certainty. We end with awe. Awe at the vastness of what might be. Awe at the precision of what is. Awe at the strange, temporary miracle of being aware, here, now. Whatever lies beyond, other universes, simulations, or truths yet unnamed, the greatest mystery remains the one inside us. And so we pause, not at the edge of understanding, but at its threshold, listening, wondering, ready for whatever comes next.